So before we start, I want to introduce a little bit of myself. So my name is Zihui Lu, and I usually go by Xavier. I'm a real-time developer at S1T2, and I mainly focus on gameplay system development, and I have a particular focus on believable NPC and companion AI development that enrich the immersive storytelling. So I worked with S1T2. At S1T2, our focus is always story first and technology second. We mainly create immersive, story-driven experience that merge cutting-edge technology with emotional storytelling. And Unreal Engine is our primary tool to bring those words to life. Our workspace in interactive installation, real-time environment, and experimental campaigns designed to immerse audience deeply and spark their curiosity and leaving long-lasting impact. So this is the agenda for our talk today. First of all, I will walk you through the project of Antopia. So let you understand why we make the decision to use StateTree with small object for our ends. And we will walk through the AI logic for ends. While this talk does expect you to have a little bit base knowledge on the StateTree, I will give you some quick refresher on it. Actually, how many people here has used StateTree before? It's quite half-half. It's kind of expected. It's nice. Then after that, I will walk you through how to set up the smart object and gameplay interaction plugin. And it offloads specific interaction logic into specific separated game smart object to let agent to interact with. And at last, I will cover a little bit about what Unreal has made upgrade on the StateTree from 5.4 to 5.5. So without further ado, let's dive into the world of ants. So Antopia. Antopia was an immersive digital experience, exhibition we developed with Museum Victoria in Melbourne. It's running from December last year to March this year. The exhibition was developed in a Unreal Engine and projected into the space. Visitors enter through a portal that shrinks them down to ant size and allowing them to experience life in the ant colony. The exhibition featured 5 main areas. There's central hub, nursery, queen's chamber, pantry, and outside. Each area provides different interactions. One of our main mechanisms shared across the room is that visitors have a pheromone trail behind them when they enter the projected area, and ants in the room will roaming around, and they will follow the visitor once it detects the trail. And in each room, we also have different interaction points. So visitor can lead those ants to follow them to the interaction point and pass them to the specific slot. And in each room, those ants will behave differently when they performing tasks on the interaction point. For example, in outside, they will be making bridge. You can see from the GIF. And in central hub, they will follow the path light ahead of them. And in nursery, they will go to tend or egg or a larvae. Another main requirement for our ant colony is, of course, ants. We need a lot of ants, as much ants as possible. So that leads us to explore the use of Mass AI. Mass AI is a scalable AI framework designed primarily for simulating large crowd or swarm of agents efficiently. It allows developers to manage thousands of lightweight agents with good performance. And StateTree is the main way of defining AI behavior inside Mass AI system. And this is where we first interact and start using StateTree. But with further experimenting with Mass AI, we decided to abandon the use of it. There's 2 main reasons. One of it is the code overhead. Mass AI is a ECS, which is entity component system. So we will need to wrap everything into fragment and processor That means like we need to take longer, more time and more effort to develop the same behavior, the simple behaviors. And another reason is, as we mentioned before, we project everything to the space. We use undisplay for that. There's some non-deterministic element in mass AI, which cause the undisplay to desync from one to another screen. So we don't have enough time to dug through the code and find out why. So we decide to abandon mass from here, but end up keeping the state tree from this point. This is our project setup in the end. Basically, each room was a game feature plugin, which means they can be loaded individually and on demand. The game feature plugin often used as a tool for things like DLC or modding support. So the use of game feature plugin allow our project to keep a clean code base and readable as well, and also avoid accidental interaction and dependency between unrelated features. But it also means the restriction of room plugin is only able to depend on the project, not the other one, and not other way around. Initially, we plan to use state tree ends in all the room other than the sequential-driven animation-focused ones. But through creative iteration, we focus on three main rooms, which is central hub, nursery, and outside. In terms of timeline and team size, we have a relatively small development team and short dev period. Basically, we have 4 months to deliver the project, and 2 programmers was working on Central Hub and the core project Antopia, and 1 programmer was working on Queen's Chamber and Nursery, and also we have a blueprint developer working on the outside. So with this, we need to try developing the room features as parallel as possible. So to sum up from what we go through for the project context, we have the following challenge. We have short dev time and small team, and we need to develop different interactions across different rooms. That means we need to work as parallel as possible. Then we need to follow the setup requirements of the game feature plugin, which is room plugin only depend on the project and other non-feature plugin. And we try to load them like the only things they need to load in that room plugin. And also we need to try keep things modular and extendable for any future creative changes. So this is the structure we end up with. This is allow developer for each room to focus only on the interaction logic without caring about the same end logic across the rooms. And we can develop in parallel, of course. And I will show you how to set up this in the rest of the talk. So let's dig into the end state tree. And before that, I will give you a little bit on the state tree, a little bit refresher on the state tree. What is state tree? State tree is something introduced in UE5 as an alternative and improvement over behavior tree. It's designed for gameplay logic, especially for AI decision-making and NPC behaviors. It combines state machine selectors and evaluators into a single framework. So next, let's have a look at our end state tree. You get it? Right. All right. Sorry for my awful humor. That's the actual end state tree we have. So you can see the tree hierarchy of states, but obviously it's pretty small to read from here. So I have a summarized version of it. We will go through step by step. Before that, I will introduce some main building blocks for the state tree. We have states, which represents a logic unit. In our example, idle will be a state, and following is a state. Then we have tasks. Tasks run when a state is active. For example, in the state of idle, the ends will execute tasks including finding a valid location to move to, and move to that location and rest there and repeat after that. We also have transitions and conditions. Transition is something define how and when the AI will move between states. For example, idle cannot jump straight away to working state. It will have to go through the following. Then from following, it go to working state. And condition usually work with transition. It's a gate when the state and transition can be activated. So for example, the ant only able to transit from idle state to following state if it's under the condition of it has find a valid visitor to follow. Next, we will go through an overview of logic of the ants. The first state we have is the initialization state. It's simply the ants will get spawn data and transit to the corresponding state defined in the spawn data. And they usually go to idle state first. In idle state, ants will roaming around the area and keep trying to find nearby visitor trail to follow. And if they find a valid trail to follow or visitor to follow, they will enter following state, where they follow the visitor around and constantly checking if the visitor have hand them over to a valid interaction point. And if so, they will interact with the object with defined behavior corresponding to the smart object they are using. We will cover more of this later. And finally, in the background and despawn state, they simply say bye to the ant colony and disappear at some place outside visitor's view. We also have fallback to idle and following to working state. Those are kind of intermediate states that let ants recover from some edge case, like lost the visitor they're following. We won't mention too much here. So let's go back to the working state. Why are we using the smart object for this? A little bit review on the challenger we mentioned. We have different room, each has different interactions, and we have a small team and need to work as parallel as possible. We need to follow the setup requirement of the game feature plugin and try to let those feature plugin only load what it needed and keep things modular and extendable. So we have explored few options. The first option is simple and plain. Just keep everything in the main and AI state tree. So why didn't we use that? That means like we need to keep all the assets in the core project and everything in the same state tree make it difficult for multiple people to work on them in the same time. Obviously, it's hard to manage in terms of revision control. And what I mean by keep everything in the core project means even for the room they don't need that project, they will have to load that logic into them and keep them there. So we kind of just eliminated option A. The second thing we try is linked asset. In state tree, you can define a state as a linked asset. Then you can put in external state tree, and the main state tree, when the main state tree enter that state, it will run the corresponding logic of that external one. So we can separate different interaction logic to different states. For example, we can keep central hub behavior, which is following the path line ahead of them in the central hub individual state tree, and same for the outside and nursery. This kind solve the issue with like multiple developer won't be able to work on interaction behaviors at the same time. They can check out the external state tree individually, but because the link asset is not able to switch at runtime, at least not with not without a hacky way. So everything will still need to be kept in the core project, and the rooms that don't need that project will have to load them as well. So that's also not the best option for us. Then we comes to smart object and gameplay interaction plugins. So smart object, Unreal's smart object subsystem employs a reservation mechanism that functions similarly to a ticketing system. When multiple AI agents attempt to interact with same smart object, they must request access through the reservation system. If they succeed, they will claim the slot and try to interact with the smart object. And it occupies that slot until it finishes. The other agent won't be able to use it until it's free. Yeah, in terms of gameplay interaction plugin, it allows you to use state tree and smart objects together to create a complete and flexible interaction system between actors. It allows state tree to handle both the logic of the objects being used and the actor that using them. So with more understanding of those two systems, we can probably explain more on this structure I've just showed you in last section. So we have AI state tree and smart object definition in the core project, and we have different interaction logic in gameplay interaction state tree only in their corresponding room plugins. That fits exactly what we need. So it fits the requirement to keep assets separate in room plugin. And room plugin only loads what it needed, and developers can work in parallel on different interactions. Now we know the structure of that, I will walk through how to set up basically the smart objects. So we were using item pool as an example. Basically, it's an interaction point we set up in Antopia. It's where ants can take or drop off item. Depending on how many items still in that item pool after they interacted, the item pool will close or open their slots to allow more agents to interact with it. So first thing first, you will need to enable the required plugin first, which is gameplay interactions and smart objects. Then we will need to set up something called smart object definition. A smart object definition is a data asset that contains the immutable data shared between multiple smart object runtime instances. It's under the category of artificial intelligence. After you create and open it, you will see some layout like this. Like Blueprint, it has a viewport. It visualizes what you have built in there. Then in then you can set up something called slot in smart object definition. In smart object definition, a slot represents a specific interaction point or location on that object. Sorry, that can be used by an agent or a player. Each slot defines where an agent can stand, interact with, or be placed relatively to the smart object. Additionally, you can add activity tags to help differentiate and help agents to filter in the slots. There's also something called preview setting you can set up. You can add actor or static mesh there. It will show up in the viewport, and just make sure the slots you set up are at the desired position of what you want to use with. Then the main thing we need to set up is the behavior definition. Smart object behavior definition contains the data needed by agent or player for the given interaction. So when an agent or player is using the smart object, this is what's getting executed. So for here, we need to select gameplay interaction smart object behavior definition. It provides a slot for you to put in a state tree. It links the state tree behavior to the project. To the smart object. Now we set up the smart object definition. We can start setting up the smart object actor. You can find the smart object component in there. The smart object can be added to any actor to make it as a smart object in the level. The component will point to a smart object definition asset, which stores the configuration of given smart object template. You can see that you were able to set up the gameplay interaction state tree and tags straight away from the component, but it's not defaultly there. So I will show you how to set this up. To set up this, you will need to go back to smart object definition. Then you will need to have a parameter for the property you would like to expose and bind to that property. Or a simpler way will just be shown here in the left corner of screen. On the right side of that property, you can select promote to parameter. It will handle the rest things for you. This kind of setup allows you to reuse smart object definition with different behaviors. So now we have the smart object actor and smart object definition. We can set up the actual logic for how the player or AI will interact with this object. From here, we will use gameplay interaction state tree. It's the state tree for smart object behaviors. To create it, it's similar to state tree. It's under artificial intelligence. So when you select state tree, it will promote you this window. But instead of select state tree AI component or state tree component, you will select gameplay interaction state tree schema. Upon creating and opening it, if you have used state tree before, you will notice this interface is pretty much the same as AI state tree. The only difference is in the context. So it exposes more parameter here, which is state tree, smart object actor or smart object claim handle. It allows you to interact with the smart object more directly. Unreal also supplies a set of pre-built tasks for helping update and use smart object slots. But to let agent to perform more complex behavior, we need more custom tasks than those. So from here, we need to set up the tasks for gameplay interaction state tree. We can implement those custom tasks in either C++ or Blueprint. It is pretty similar to set up the general, pretty much similar to set up general AI state tree task. So before we jump into game interaction one, I will just have a quick refresher on how we develop a general state tree task in C++ for the general AI things. First thing you need is instance data. So instance data is a custom pre-instance storage used by that task node and when it's executed at runtime. It enables each running copy of the task to maintain its own local state rather than sharing it across all use of that task class. Then you will need to have a structure for implementing your task. It's normally inherited from state tree task common base. And in there, you will need to define what pre-instance data structure this task will use. Then you can put corresponding logic into the function you will need. There's three functions you need to implement, or you can implement. There's enter state, tick, and exit state. Enter state called once when the task starts, and tick will be called every frame when the task is in running state, and exit state will be called once when the task ends. So now we know how to set up the general state tree tasks. Let's have a look at the gameplay interaction ones. At a glance, you will see it's pretty much the same. It's the instant data you will first need. Again, the only difference is what you expose in the context. For the gameplay interaction ones, you will have something like smart object actor, and smart object claim handles like this. So for reference here, the smart object actor is the actor that contains the smart object component. And the actor is what the actor or agent that interacted with that smart object. Then that's the task implementation part of gameplay interaction state tree tasks. Again, it's pretty much the same as the general ones. The only difference here is it's inherited from gameplay interaction state tree task instead of state tree task common base. This helps you to manage the scale of those tasks. The tasks that inherit from here will only show up in the gameplay interaction state tree schema. You can also set up the gameplay interaction state tree task in Blueprint. But Unreal haven't support gameplay interaction state tree task base in Blueprint. So just select Blueprint base as parent for start. But just to remember it, to naming or categorizing it carefully to differentiate them from the tasks that use for the state tree AI. Now we know how to set up the task for gameplay interaction state tree. Let's go through the logic of item pool for reference. For item pool, the first state they enter is simply just to find what slot is currently being used by checking the tag is either drop-off slot or pick-up slot. Then it will transit to corresponding state. The corresponding task flow for the slot will then be executed. It's either, for the first part, is end pick up an item, and the second part is end drop off item. So one of those logic flow will be executed. From either logic flow, the state tree will end up in the state called updates slot status. It basically open or close the slot to enable or avoid agent to use it depending on how many items still left in that item pool. And here I will also quickly showcase some other gameplay interaction state tree for each room interaction point. This is end bridge in outside. You will see it's simpler than the one than the item pool. It doesn't have to handle changing the state for the slot because it's only have one slot, and smart object subsystem will handle this for us. And this is the state tree for an interaction with egg or larvae in nursery. And this is the state tree for ant following path in central hub. So with this, we can put those behavior logic in separate room plugin. Now we have the behaviors for all the smart objects ready to use. We need to tell ants to use them. And before that, I will just quickly walk through the smart object basic logic of how the AI will use them. So when agents want to find and use a smart object, they will search in the whole world for if there's any smart objects in this world. If so, they will filter and evaluate by tags or status, tags and status, to see if there's any available ones for them to use. If so, they will try to claim the slot of that smart object, then execute the smart object logic. After they finish interacting with that smart object, they will release the smart object for other agents to use them. Then to create tasks for using smart object for our ants, we will need to interact with smart object subsystem. The smart object subsystem is responsible for keeping track of all smart objects available in the level. Smart objects are automatically registered with the subsystem for access and tracking. This subsystem is automatically created in the world when you enable smart object plugin. And it supplies a bunch of functions shown here, like allow you to find, claim, and use the smart objects. So to creating tasks for ants to use them, basically we need to create corresponding input and output in the instant data of the task, and just call the function shown here in the task implementation. For example, if you want to claim a smart object, you'll need to have the smart object candidate slots and smart object claim handle stored inside the instance data. Then in the task implementation part, you will just simply call mark slot as claimed from the smart object subsystem. Use smart object task is a little bit different since we are using the gameplay interaction plugin. You will need a smart object claim handle as an input, and also keep a gameplay interaction context as a property. We will need to call mark slot as occupied from smart object system and custom into gameplay interaction smart object behavior definition. It's very long. And from there, you can pass all the information from your claimed handle input into the gameplay interaction context. When this all set up, just simply call activate the behavior you just cast from mark slot as occupied and activate it from the gameplay interaction context. And in the tick function, you will need to keep call the tick on gameplay interaction context. And when the task stops, you will need to remember to deactivate the context as well. So with those tasks, we can use them to build the logic flow of how the ants will use them. Basically, they just, so we don't have find smart object. Basically, they get information from the visitor they follow. Then they will claim the slot and try to use them. So that's basically complete our structure of this whole smart ant system. So in the code project, we have the end logic. So from the end side, they only need to know the logic of if I have a valid object to use. And from the room plugin, we keep all the interaction behavior logic individually. And from those objects, they have the logic of, from these objects, they have the logic of how the user will be interacted with me. It's pretty much it for the setup. So let's give a quick summary on the smart object and gameplay interactions. We have set up the smart object definition. It's a data asset that contains an immutable data shared between multiple smart object runtime instance. Then we have set up the smart object component, which points to the smart object definition and stores the configuration of the smart object template. Next, we have set up the gameplay interaction state tree, which contains the logic of how the actor will interact with me from the object's view. Then we have developed the tasks for AI agents to search, claim, or use the smart object. From there, we have built pretty much constructed this modular and expandable structure. So what's the benefits from it, and what are some potential use case? Again, this is help us a lot with its modular and extendable structure. Some use case, like you can just extending the interaction behavior really easily. For example, you have set up some interactive object in your project. With this setup, you can easily just keep adding new different interaction behaviors by only implementing a new gameplay interaction state tree and apply to it. Also, the fact that it's able to work well with game feature plugin, meaning that you can apply this setup with your DLC or modding development. That's pretty much it for our setup. Then for the last bit, I want to cover a little bit how the state tree has been upgraded from 5.4 to 5.5. I know that we are in 5.6 era now, but it's not there when I still make this talk. But like the new feature is still carried on to 5.6 and it's still useful. So I'll just go through them quickly. One of the new things they have really useful is the custom payload structure. So in 5.4, you can only send tags to trigger events, but in 5.5, you can send this with a custom payload structure. To use our end's initialization state as an example, in 5.4, we have to send a tag trigger. Then it enters a state to retrieve initializing information from the actor. Then from there, it transit into a corresponding logic flow. But in 5.5, with the custom payload structure, we were able just to send a trigger with that payload and transit into corresponding logic flow straight away. So this is like more efficient in 5.5. And we also don't need to store any information in actor, strip all the logic of the state tree completely from the actor itself, make it more reusable for different agents. It's pretty simple to set up the custom payload structure. You will just need to have a use struct that contains all the information you want to pass around. Then call the send state tree event with the tag you have defined. Another thing have been added is state tree property reference. So if you have used state tree, you will notice state tree have a parameter section. But those parameters are read-only. You can only define it once, and you won't be able to change it at runtime. So previously in 5.4, we keep all our writable parameters in our actors, which means the state tree can only work for specific actor or agent and those inherited from them. But in 5.4, with the function that we can have those writable parameters in state tree, again, we can just strip the logic away from the actor and make it just more modular and reusable for different agents. It's pretty simple to use for in C++. You just need to use the state tree property reference to reference a parameter you want to use. And you can read it same as how you read other pointer and references. And same as the write back into it as well. So Unreal also supplies Blueprint API for state tree property reference. You will just need to set up a variable in task by selecting state tree property reference and set reference to the structure you want to use under the default value. Read and write by calling the node get property reference in the blueprint. And starting from 5.5, state tree also have better UI. So you can see all the tasks is not stacking together anymore. It provides better readability. One improvement I really like is in the menu where you can select the state you want transit to, you can see the whole structure of your state tree as well now. So it was something we struggle in our project. We have a lot of same name in the substate, and due to our poor naming, it's really hard to find and debug. With this structure, so no more struggle with that anymore. Another new thing have been introduced is outliner. It's a summarized version of your state tree and allows you just to pick and jump to the exact state. And obviously, there's more new feature, especially with debugging. They have added breakpoint and state enable disable in 5.5. This allows you to debug your state tree and change its behavior without recompile or deleting things. Obviously, there's like more new feature like parallel task, everything I haven't really looked into. But in general, it's becoming a more powerful tool and framework for agent behavior development. So that's it for this talk. Let's do a quick summary. In this talk, I have walked you through how we make the technical decision on using StateTree with smart object to implement our end behavior with a scalable and modular architecture. We know how to set up the smart object with gameplay interaction plugin to achieve decoupling interaction like carrying food, tending eggs into smart objects that make system more modular and scalable, extendable. Then at last, I have covered some UE 5.5 plus feature, and it's becoming a more powerful and maintainable tool. So even though StateTree is not like fully complete yet, obviously Epic is making a lot of new updates and improvements in upcoming and recent releases. But the fact that it's able to make a really clear structure for AI behaviors, and it's really easy for debugging and just easy to understand, it's becoming a more powerful tool. So either you're managing like the chaos of ant colony or just try to find a clear structure for your AI development. I hope this talk have provide you some reference point of how and when you can choose StateTree and small object for your project. And that's it for my talk. Thank you for listening. So, any questions? Yeah. Like, sorry.
Are there any key architectural?
Sorry.
If you were redoing the project now, are there any architectural changes to how you would use StateTree now with the benefit of hindsight?
It'll probably be like whole different thing because they have added a lot of feature in 5.5, especially like how they, like I mentioned, strip the logic from end itself. So I will probably just develop like a more scalable and like modular system from it. And also they have provide like parallel task things, which we kind of needed before, but wasn't there. So probably will be whole difference and that's in fact like how the StateTree's current like status is. It's keep upgrading in each release of agent version. It will be a little bit hard to keep tracking and try to keep your project up to date, but I guess it's just keep in mind this is a really good system for future use to consider for your project, especially for the AI thing.
Thank you.
What else? Thank you very much. Yep, all good. All right, thank you.